Hello, hello. Let's start. A very short stream today, I guess, just to keep our uh, streak rolling, I guess. Streak of almost 2 weeks streaming non-stop, maybe actually already more than 2 weeks. So yesterday we implemented brake resistor control and also updated the Core PCB. And today we have actually only a single task to implement, which is watchdogs. But maybe we will also touch on space vector modulation. Not sure, we will see. And how will we implement watchdogs? I think I will show you the true bare metal way. And the true bare metal way is to go and start reading reference manual. So this is the true bare metal way. So let's see. What do we need? We need STM32 G4 reference manual. And here we need to find our watchdogs. First. So I think we have two, and we need to figure out what they do. And when you work with bare metal, how you do this is by reading the documentation. Or at least this is a general way, because nowadays people just ask AI or watch a YouTube video. But reading documentation is very useful. Even if it's not the first thing you do, I would still highly recommend doing this. So let's see. No, 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 no. Actually, this is kind of curious peripherals that I would like to test later. But for now, we are not interested. No, 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 no. Still no. These are the ones. And they are very short. They're incredibly short, so this should be a very fast implementation then. I just never worked with watchdogs before, so this will be my first time implementing them. Let's do this. So let's hide this and let's see what the documentation tells us. Okay, embedded with the peripheral, offer a combination of high safety level, timing accuracy and flexibility of use. The peripheral detects and solves malfunctions due to software failure. Okay, that makes sense. It's a very basic idea. By its own dedicated low speed clock and stays active even the main clock fails. Okay. Sure. So main features, free running down counter, okay. Clock from an independent RC oscillator, okay. Conditional reset if the watchdog is activated when the down counter value becomes lower than 0. Okay. If the down counter is reloaded outside the window. What is outside the window means? Not sure. So it has prescaler, sure. When the independent watchdog started by writing the value. Okay, so let's start implementing right away. I would imagine that every single project we have with G4 will benefit from having watchdogs. So let's do it in the SDK that is common between all of them, all of the projects. So let's say watchdog if h. Very nice, very nice. And let's start by void if setup independent watchdog. Oof. And I would imagine that we will also need something like watch dog set. Probably also void. Not sure. This will be question. So let's also make a C file. So this is how all of these files were eventually created in the past. This is how you design your SDK for anything you work with from like very scratch. You just do it. And I'm not ashamed of showing that I'm not confident in something, that I don't know something. This is absolutely fine. We start there, every one of us, at some point. We are not born with knowledge. Watchdog. Okay, and this will be our implementations. Double functions. And maybe reset actually can be a static inline, because I would imagine it will be a single call. Static. Oh, I see. Sure. Let's include something. Device. MCU includes. Now you should see the static force inline. Static force inline. Very nice. Let's put it like this. Because we don't know what will be here yet. So let's see. When the independent watchdog is started by right. Okay, so starting the independent watchdog will be IVDG KR equals to this value. So this means start the independent watchdog, because this is what the documentation just told us. Let's also see if this value is somehow existent already in CMSIS. So let's see, EG, KR, key. Okay, so they already have it implemented, right? Okay. Do they? No, they don't seem to be. It doesn't look correct. 0x000 CCC. Nothing like this, just CCC. Also nothing like this. Okay, so they don't seem to have it implemented then, because this is not it. This is not what I expected. And therefore we will get our value back and we will do a to-do make a definition for the value. Definition. Very nice. So then the counter starts counting down from the reset value of 3f. 3f is not much at all, actually. 3f is just 256 multiplied by 16. It's 2 in 12, so it's 4096. That is not much at all. Is it 4000? Let me double check. To not spread lies and misinformation. So 3Fs. Yes, it is. Okay. When it reaches the end of the count, the reset signal is generated. Whenever the key value is written, the value is reloaded and watchdog reset is prevented. Okay. So to reset the watchdog, what we need to do is just IVDG PR equals to this value. And this will just reset the watchdog. To make a definition for the value. Okay. Once running, the watchdog cannot be stopped. Very interestingly. So if we are messed up in some way, we will feel it. Okay, makes sense. Window option. The watchdog can also work as a window watchdog by setting the appropriate window in the window register. I have no idea what window is for now. If the reload operation is performed while the counter is greater than the value stored in the window, a reset is provided. If the reload operation is performed while the counter is greater than... Oh, I see. So you reset it, and you set an expectation that it's supposed to be run, let's say, like in 1 to 2 milliseconds. And if it's run like in 0.5 milliseconds, it's also an error. What that was window mode means. Okay, now it makes sense. Okay. Educational. Default value is 003F, so if it is not updated, the window option is disabled. Makes sense. Makes sense. Let's then make another function, set up independent watchdog windowed. So we call one or the other. And no, it will not take this value. It will take... What will it take? It should take uint 16, I would imagine. I would imagine target window. And I need to write a comment for the function like this, because this will be important thing to explain. And I would imagine that here we need to check if the target window is bigger than this. We set like we basically need to actually return the error. So sorry, let's include debug utils, and let's return the if error code here. And what error code will it be? The error code that will be, let's just return something. Can we log also error? We can. So then let's return log error of 2 like that. And also make to do add proper error code. This means that the window mode is disabled. So let's make sure that we still write the register, just in case it wasn't set to default. So let's write this value with a 0 so that we have a nice style. And else, if this is correct, we just set the register. Like this. We set it to target window. And we also start the watchdog. Okay, that was quite a fast implementation based on 2 paragraphs of reading. 3. So let's see. Let's see. So configure watchdog when the window option is enabled. Oh, hold on a second. Enable the watchdog first. I would imagine I still need to enable it here. So it should happen no matter what. So we enable the watchdog, enable register access by writing 5.5 here. Okay. Right, scalar. Interesting, interesting. So let's say what's the register prescaler equals to question mark comment. To do right prescaler. And I need to understand how do I decide what scalar is. Not obvious to me yet. Write the reload register, but what do I write here? Like, what the hell? Okay. Was? Also, is watchdog the peripherals that I need to clock is another interesting question. So let's actually see if we need to clock the watchdog. And we can see it by just scrolling through the registers when we have a clock enable ones. Not this, not this, but not reset. Start when it enable. Reset still. This is ENR. So CRC should be enabled, Flash should be enabled, FMAC, Cordic, DMAMUX, and DMAs. No. RNG. Okay. IS, DAX, ADCs, GPUs. Nope. QSPI and FMC. Nope. Power, FDCAN, USB, UART, SPI, windowed watchdog. Is it a windowed watchdog or what is it? VVDG is system window watchdog. Okay, but we have an independent watchdog. So do we need to enable the clocking for it? There is no enabling here. Here's the P, LPUART, I2C, still enable, high resolution timer, no, new, SPI, start timer, SPI, start, system, okay. Still enables, CRC, SRAM, Flash, Cortex demos, okay. Okay, this is also in sleep mode, so this is some kind of repeat. So I would imagine that the documentation saying that it has its own clock means that it always runs when we enable it, so we don't need to enable clock separately on any buses. Okay, that probably makes a lot of sense. Probably makes a lot of sense. Let me a moment. A moment, I'm ready. So wait for register to be updated. So it should be, so I need to write something here, which I have no idea what yet. And then I need to wait for the register that is SR to be equal to 0. So while it's not equal to 0, we wait. Okay. So it wait for registers to be updated. Write to the window register, sure. This automatically refreshes the counter value in the reload register. Write to ring, and this is the end. Okay. Writing the window value allows the counter value to be refreshed by the PLR when the register is set to 0. Okay, sure. That makes sense. So does this make sense then? Yes, we still write this value after all, and we still enable the watchdog here, unless we don't. Unless we don't enable the watchdog with an incorrect setting. Also, maybe this setting should be automated outside. So actually, let me, for now, just do it like this. I will just set this value here, because I would imagine that we will redesign this later. Redesign when I fully understand how to work with the watchdog. Okay, configure the watchdog when the window option is disabled, so this function. Okay. Enable the watchdog by setting this. So, okay. This not starts, but enables the independent watchdog. Okay. Enable register access. So same thing here. Do I need to do two knobs? I would imagine this would make sense. Maybe, maybe not, because at least for all the RCC registers, reference manual requires you to do two knobs. Otherwise, you can possibly catch a bug when your registers are not available for write, but you write to them. And actually, this was a bug with encoder DMA setup we had like a week and a half ago or something. It was very annoying, and we were looking for it for like 2 hours. So let me actually to do check if this is needed. And how can I check it? For example, by looking at hull code, or by finding this place in the documentation. So these are valid options always. So then we enable register access, and then given that I do it here, let me actually also copy it here like this. So this will be enable register access. We copy it here. Okay. Write the prescaler, so this line, and write the reload, which I also still have no idea what it means. Wait for the register to be 0, so this line also comes with us here. I need twice this to do. And then refresh the counter value with was. Oh, wait. Oh, I see. So we need to refresh it as well. Sure. Sure, why not? I have a phone call. let's continue. So, low power freeze. Depending on the stop or standby options configurations in the flash option bits, the watchdog can continue counting or not during the stop mode and standby mode, respectively. If the independent watchdog is kept running during stop and standby, it can wake up the device from the mode. Refresh the user protection bytes section. Interesting. Oh, there are quite a few of them. Very interesting, but we are not working with low power modes yet. So, register access protection. Write access to this register is protected. To modify them, first write the code. This, which we were doing. Okay. In the keyr, write access to this register with a different value, break the sequence, and register access is protected again. Makes sense. This is a case of the reload operation. Sure. So reload operation forces us to close these registers for writes. Makes sense. Debug mode. When the device enters debug mode, core handled, the watchdog counter either continues to work normally or stops depending on configuration is a corresponding bit. Okay. This is all. This is the whole documentation for watchdog, two pages. What? And I still have no idea what to write to PR and like LRR. Okay. So keys, sure. PR, prescaler. They are written by software to select prescaler divider. Reading from the counter clock must be reset in order to be able to change this. Reading the register returns the prescaler value from the VDD voltage domain. The value may not be up to date valid if write operation. The register is ongoing. But what is the clock frequency? What is the frequency clock? Let's go to the datasheet. STM32, G431, datasheet. So let's see, and let's EVDG. Okay. The bit was expressed on 12-bit down counter and an 8-bit prescaler. It is clocked from an independent 32 kilohertz. Okay. Okay, so I think we will have to modify this. So let's prepare a section because we don't have anything watchdog related here, right? Yes, not yet. So let's find a cozy place. Sorry. Okay, this is ADC, APAMPS, Cordic, FDCAN, FDCAN, FDCAN. Oof, quite a lot of stuff in the FDCAN. Let's put it to the end actually. And this will be IVDG, enhancement definitions. So what we put here are, so let's define IVDG. Actually, no, it will be clock frequency. And this clock frequency will be defined as clock frequency hertz. We should always specify the measurement value. So, and this will be 32,000. This will be unsigned integer. So 32 kilohertz, always the same. Then defined. I would imagine prescalers are defined correctly. Let's test it. So the PR register has a single point, which is the prescaler value. So we can write directly to it, given that we have no risk of overwriting everything, because everything else is reserved, and reserved is not important, so we can write any value there. So let's see. It will be IVDG. VR. Let's see. Oh, this is awful. So they are not defined. Sure, let's define them then. So actually, I would imagine that we don't have definitions like this here. So I am better off putting it into this file together with all the keys and stuff like this. So it will be define IVDG enable what? Enable watchdog timer or clock key. It will be a key and the key will be 0.00. So let's put it inside. Let's copy this here. And also let's move this here. So we enable the clock with a key. And we will also have another key. Define and enable register key. ACC is access. And how is the word access is spelled? With to see. Okay. Okay, all right, sure. So this will be this value. Very nice. Okay. Let's put it into our code. We also need to define IVDG max value counter value, or rather, yes, this is fine. Yes, it is fine. So let's put it like this, which is equals to 4095. And here we also need IVDG. It is set watchdog key. Let's put it like this. And here. And I think this is all we need. And here, do we need anything? No, this looks fine. Now, regarding prescalers, now that we know that we are 32 kilohertz, we can think. Oh, and the minimal possible value is 4. So the minimal value, the minimal time duration that watchdog can run for is at 8 kilohertz, which is rather not that fast, given that our PWM currently runs at 20 kilohertz. So I would imagine that this is fine. Do we need a table? I don't think so. We just need to do registers. Let me find an example of something of similar design. I see. So this will be then IVDG, VR, divider 4. A moment. Let's continue. And what will be the postfix in such case? Divided by 2. Oh, this is kind of awkward. PR. It's kind of supposed to be like this. PR divider by 4 divider 4. And I really don't like how far these values are. They don't need to be that far. This will be 0B00 0 for easy accounting. So let's see, this will be 8, this will be 16, this will be 32, 64, 128. And there are 2 options for 256, but we will only add one of them. So, all right. 1, 1. 1 here. Okay, so there is a gap. No, there is no gap. No, there is a gap. Was 3, 4, 5. Oh, no, there is no gap. 6. Okay, makes sense. Now, how do we set it up for a project, for any project? Like, how would a person decide what the frequency they run their watchdog at? It can be a function call. We can say we would like our watchdogs calls be not quicker than, let's say, every 1 millisecond. And then we can very easily calculate the frequency at which we will have. Like with the prescaler, we need to select. Actually, let's do this. I like this idea a lot. I rather like it a lot. So let's assume that for our watchdog, we decide the frequency based on minimal duration. So in minimal duration, we will put in as uint 32t to be min duration microseconds. So let's do it in microseconds because we can have 8 kilohertz, and 8 kilohertz will give us 125 microseconds, which is the fastest it can work. And let's do... Oh, so... But this will not work for windowed watchdog. And windowed watchdog, how will this work? We definitely still need to provide this. Let's say I watchdog, because the function names are too damn long. So we will need to provide this. Very nice. But also, what do we need to provide? I would imagine then the window now should also be a time. This should be a max duration. I'm not sure, I'm not positive I know how to implement it yet, but I think this is a right concept in my mind. And I think this function is already done. Watchdog I reset, so it's independent watchdog. So let's get back here and let's apply our name changes. So the concept here is very clear, but the implementation is not. And now we make a design choice in our whole-like implementation, because like all these P files are like my answers to whole that I wrote myself, so that I have better control and better understanding of what I'm doing. And now, I need to decide how I will use it. And I think this way of using it is kind of nice, because you are positive that this will never be not doing what you want to do. Oh, yes, this is very nice. So now we still need to do this. I still need to check what is that. And now at this point, we need to decide on upper scalar. And let's say our int 32t current frequency will be equals to, default value is 8K. Correct? Correct. So it will be, how do we make it in a readable way? It will be this value divided by 2 to the power of the PR divider by 4. This makes absolutely total sense. I don't think I need to add this. So, and now we say what? While, so duration is in microseconds. And we need to do int32t current duration will be equals to 1 million microseconds in a second divided by current frequency. Right? Let's say sec to, okay, and where I define seconds to seconds, let me see if I can include this file. Sec to use sec is defined in timing. Timing is here, and timing is in Cortex utils. That's unfortunate. I actually think this should be moved. Right? Should it be moved? As int. Let me temporarily include it. Whatever. Let's actually leave. This will be beautiful, but let's leave just million here. And add a comment that it's 1 million microseconds in a second. So this will give us current duration between watchdog resets, the maximum duration that it will have. And at 8 kilohertz, this will give us exactly 125. Let's say we want not 125. Let's say we would like to have 1 millisecond or more than 1 millisecond. Then we need to have a cycle while yes, and we will, no. Let's do it like this. Int32 current scalar equals to this. Formula is correct. I don't think it is a right comment to have, because it is actually also wrong. That would have been a banger. Formula is correct when it is wrong. Oh, that would have been such a nice bug to have. This is 0, right? It is 0. So we need to left shift by 1 to get 4. And here we define by current prescaler. And we do while current duration is smaller than min target. Okay, let's actually call it not. No, let's call it min duration. But let's call it min target duration. The names are a bit long, but that's all right. I'd say that's all right in my book at least. So while it is smaller than min target duration, we need to increase and also. And current prescaler is smaller than 256. Actually, we will put, oh yes, this is very nice. 256 like this. This is much more readable. What we do is we current prescaler we shift it by 1. If you never saw the syntax, actually don't sure if it works. Actually, oh, it does work. Let's remove this for now. So this is the same as doing the shift operation here with equal sign here only. Makes total sense. So we do this and we recalculate current frequency, which is equal to do we even need to recalculate actually? Let's see, let's do it. Why not? This will be run once. So we do exactly the same calculation actually. Like that. And then we update our current duration. Current duration equals to 1 million. 1 million, correct? Current frequency. Let's add a note that it is 1,000,000 microseconds in a second. Right, proper number of zeros, perfect. So this should give us a final value. Should it actually? Hold on a second. No, we need to store the prescaler separately. So the prescaler will actually be, aha. So will it be called the prescaler then? What we need to do is we need to start from 2 plus PR divided 4, which is 0. And we need to add 1 here, plus 1. And we need a separate variable for the division. So then we will need another variable, which will be current divider, which is equals to 1 shifted by current prescaler. And we use a divider here. That makes much more sense. So, okay. Some of these variables will be out, automated removed by the compiler, and we just doing it in a readable way for the future ourselves or anyone who would like to read and understand our code. So current divider, we can just do this operation all the time because it is a single clock cycle operation no matter what. So we use divider here then, and we divide here by frequency. And now we use our prescaler -2. Scalar -2. And we do it in a correct CMC style. We do FDG, PR, PR, pause. So we move it to a position of the register, and the position of the register is actually 0. So we can skip it, but we will not, because we are good guys. We are smart guys. Okay, I like it actually quite a lot. And now we're going to see that we will not trigger quicker than this. And also 1 millisecond is a viable option. So we might as well do this. And the duration can be set up in the define file, our define file, which we will do after we test this works. So how do we test this works? It's very simple. Let's first make sure to finish up our function. We need to do something here. So reload register watchdog counter reload value. These bits are write access protected. They are written by software to define the value to be loaded into the watchdog counter each time the value. Oh, okay. So we also can start from a different location. Wait a second. Hold on a second. What am I doing? What am I doing? Because, oh. So this value will be obtained by multiplication of the prescaler and this value, because this value. Oh, so the watchdog can work for seconds before reset. Is it the correct behavior then? Like, should we allow our watchdog to wait for like seconds to reset ourselves? Reset our device? I would imagine this is the case, right? But that complicates things quite a bit, actually. That complicates things quite a bit. What can we say? We can say that our watchdog setting is set up in milliseconds. And then we actually skip all this loop hopping with clock setup. Let's actually do this. This will be so much easier, right? Counts down from this value. The timeout period is a function of this value as a clock prescaler for timeout information. Bit must be reset to be able to change the value. It returns value from VDD voltage domain. Okay. Sure. Sure. Of course. Sure. Sure. Of course. Sure. Sure. Yes, we will actually change the way it works. So the function can set watchdog period with accuracy of 1 millisecond up to 495 microseconds. So then if this value, oops, target duration US is higher than this value, we have an error, which we have to log, and we will log it successfully. But we will not return, we will just set it to the maximum value. Actually, we just put it here. And also, we should put this here. And continue from here. I think this is the correct way to handle this without an error. Like without an error, we return, because setting watchdog incorrectly on the high side is not critical as long as it resets. So we might as well do it. Okay, we set it like this. Then all of this actually goes to hell, and we just set our prescaler to 32, which simplifies things a lot, actually. And also, yes, we just do it. Just do it. IVDG dot, no, it will be PR, and it will be divider 32, and we still move it to a position to be good guys that following guidelines. And here we just write our RLR. Again, that we already checked the value. We can just write it as min duration moved to IVDG RLR PL pos. Very, very nice. So let's make them on the same line just for the beauty's sake. And why not? Let's make it also on the same line. And this. And that. So I think this is it. I think this is the implementation we have. Oh, and it also makes the windowed implementation very straightforward. Now I can actually see it in my head. Okay, this is very nice and very easy to set up, actually. But let's say status register. Watch the counter window value update. This bit is set by hardware to indicate that an update on the window value is ongoing. It is reset by hardware when the reload value update operation is complete. Okay, not useful for now. Watch the counter reload value update. This bit is set by hardware to indicate that an update of the reload value is ongoing. It is set by hardware when the reload value update version is complete. Sure, also not important. Watch the okay, so none of them are important for now for us. This register, and this is all. This is so easy, actually. And like bare metal development is not scary. Yes, you probably could have gotten like not actually this. Like if you were to do this with AI, you would have no idea how to understand it. And as you saw during our 1 hour of implementation, we actually went through 3 different philosophical approaches on how to measure it. And this is quite important because we finalized on the approach I like, and that is nice and easy to understand. So yes, we will have like 1 hour more to test everything, to make definitions that are needed. But other than that, it's just very easy. It's very simple and very straightforward. And you don't need AI to do this, which is the most important thing. And you will also understand it better. And no, I'm not saying that AI is useless. I'm just saying that you might as well be able to do it yourself. Now that I decided that I will have a 1 millisecond step, it makes so many things so much easier. So we can do the same checks here, like we can just copy and paste everything, but we also need to update the function name. and we will not return the error here. We will just log it, which will be a more correct approach. Okay, that makes sense. So we do the check, the same error. We do another check. So if our max target duration, okay, so if this target duration is shorter than our mean target duration, we also have an error. Because otherwise it makes no sense. And if we call an error, we can just, oh, I see how I'll do it. I will just call this function. Very nice. And this will be so easy. And I will just return, but also I will log an error. Ooh, this is so nice. So nice. Okay. So what else? This stays the same. We have an access key. Remove. Remove. Enable register access. Sure, this stays. All of this stays. This error check stays. Very nice. And then we write this. Was. What do we? I need to watch it up. Look it up rather. And we just write our target. Mean target duration. Now it will be max target duration. Here, and we move it by IVDG. And the register is WinR, and we will have a position here. Very nice, very nice. So absolutely amazing. Okay, remove it here because we edit it by accident, not by accident, but by in the part of our investigation process. So this is fine. This is not needed anymore because the name of the definition tells for itself. Same thing here. We don't need any comments we may remove. They will be unnecessary and will only bloat our code. Sure. This looks very nice, actually. Actually, very nice. Now comes the part when we test it. And the part when we test it comes like what? Also, there was a register. And I need to quickly look it up because what will happen in the debug mode? I don't want my device to reset in the debug mode. This is very important, and I hope it is default value. Actually, let me go and get more water. One moment. I'm back. Okay, so now we need to test it. And to test it, okay, I remember I was looking into the debug mode and also to see this approach. Do I need to write the key here? I don't need to write the key. Don't need to write the reset because writing window updates RLR. Okay. And now where is the debug option? 22, debug mode. Freeze register. So let's go to our other open window and let's look for it. Like, what the hell is that? It is not here. Oh, it is a datasheet because it is a datasheet, of course. So, and let's see MCU debug component. So helps the debugger provide support for low power modes, clock control for timers. Okay. And what is the register name? The IVD counter either continues to work normally or stops depending on the configuration of the corresponding bit in the freeze register. Freeze register. So, oh, this is like one-liner. Okay, let's see. Oh, wait a second. Let's actually read it. It looks. Oh no. It looks actually kind of important. MCU debug component has to debugger provides support for low power modes, clock control for timers, control for the trace pin assignments. To answer the low power mode, the instructions must be executed. The MCU implements several low power modes which can either deactivate the CPU clock or reduce the power of the CPU. The core does not allow something to be turned off during a debug session as these are required to debugger connection. Okay, makes sense. During debug, they must remain active. The MCU integrates special means to allow the user to debug software in low power modes. For this, the debugger host must first set some debug configuration registers to change the low power mode behavior. We are not interested in any of this. It can be written by the debugger under system reset. If the debugger host does not support these features, it's still possible to write the registers by software. Okay. During a breakpoint, it's necessary to choose how the counter of timers RTC and watchdog should behave. They can continue to count inside the breakpoint. This is usually required when a PWM is controlling a motor, for example. Okay. They can stop to count inside a breakpoint. This is required for watchdog purposes. Yes, exactly. Also, actually, now that I'm reading this for the first time, I'm quite curious at what are the default values. So let's see. Debug sleep means what? 0. But I don't care for sleep standby or anything. Trace mode. Oh, okay. I think trace pin assign control. Asynchronous mode. Also not something I understand how to use for now. So let's skip it. Here. Debug timer stop, and the default value is everything 0. And 0 means the same behavior as normal mode. What it means? I wonder what it means. Actually, I actually wonder. Okay. Was? It's all? And I was? Trace point microcell. No, it's not what I need. Oh, I see. Independent watchdog counter stopped when core is halted. The independent blah, blah, blah. Independent watchdog counter clock continues even if the core is halted. Not the behavior I like. This is the behavior I like. And this is not a default one. Okay. So let's say if we are in a debug mode. So if def debug and if we are in the mode when debug connection is enabled, we need to dbg MCU. Oh, this is a thing. APB 1 freeze is either 1 or equals to dbg MCU APB 1 FCR 1 dbg IVD stop. So make sure that independent watchdog is stopped during the bug stop to not reset the MCU in a long debugging session. By long, I mean longer than 4 seconds. Let's add the same here. And now let's go back and what I wanted to read, nothing at all actually. At this point, I would read nothing at all. Let's test it. Let's test it. First, let's say I would like to set it up to work 100 milliseconds just for the convenience of the testing. Actually, 1 second is all right. I don't want to break any code, so let's actually test the implementation in a different location. So let's go to, for example, bring up. So bit configuration setup to bring up. And let's go to the example 0 that does nothing and can be used as our testing platform. We were testing something, but I'm sure that it's already not important because we already tested this properly. So let's say if setup clock, system clock, and I would imagine this is all we need. We don't actually even need this, but with system clock, we can do dummy delay, the duration of which we will know. So now let's say pif setup watchdog, watchdog, and this will be, let's use it in not windowed mode. And let's say we would like to have 1000 milliseconds. Sure. Also, actually, let's set up if set up LEDs. How will we test it actually? And let's say LED 1. Hello. Toggle. Was? Oh, okay. It is GP LED 1. I actually think it's kind of unnecessary, but whatever. Let one turn on. Let's think about it. So we just set those up. We turn one on. And let's say we expect that dummy delay usec to, okay, it doesn't have it included. which is fine. Let's just include it. Break resistor will be here because we changed it yesterday while implementing the break resistor. So let's include our timings was, oh, it is included, but why do we not want to see the truths? Why do we not want to see the truths? You sec. Was. Oh, maybe because it's just not called. Let's go to main. This main by that main, and let's call it. So now you should, whatever. Whatever. Let me just copy it. Oh, because I'm stupid. Who'd have thought? Who'd have thought? Okay. Because I am stupid. And here let's do GPIO LED 1 turn off. So we will reset it after 2 seconds, but given that we expect our watchdog to reset our MCU, we will not see the reset itself. At least this is what I would imagine would happen. So let's test it and let's see if it is the case. So I think we just need to flash it and make a visual view of our LEDs. So let's see. Okay. Let's just flash our bring up. Of course, it will not because my debugger is not connected. Bring up. We have errors. Why? Because we haven't included this file. That makes total sense. Let's build again. Okay, now it works. So let's flash it. And let's see. So the idea is that D1 will be always on because our device will just keep resetting. So it is on, so it works. It works because we see a flash on D, and D is flashed because the pin the D2 is connected to is one of the MCU pins that are on by default in the default state. So given that it flashes, it seems that microcontroller resets, and there is a very short duration of time between the start of the MCU and this pin being enabled so that it's pulled low and used as a pin. So we make like we are guaranteed to see that this works after my camera will restart. So it flashes roughly 1 per second, which is exactly what we expect. So this works nicely. Now let's test if a reset every 500 milliseconds will make sure that D2 is not on anyway, anytime at all. Let's not remove this. I just need to do that and to also switch this to toggle. And let's do a quicker toggle so that we can see. And also, let's add a dummy delay here. sec to sec for 2 seconds, that we are sure that there is some time before blinking starts, so that we know when reset happens. This is actually a good thing to do, to see it. And here, let's say our watchdog I reset. So let's flash it. And this time we should see reset after. What's wrong? Oh, I see. My bad, my bad. Okay, so let's flash it. Let's run it. So in 2 seconds, it should start blinking. And it should never stop. So yes, if the watchdog were to reset, we would have saw it as a 2 second like turn on, because this is what happens after reset. So we know the device is not turned off, which proves that this works. And let's also do what exactly? I actually think that those can be implemented as like actual actionable, seeable examples for the watchdog peripheral. And it will be very nice. And actually, I will add a to-do, implement watchdog examples. This is for myself. I will probably make it off stream. So now let's see the windowed mode. Let's make sure it works. So I actually think in windowed mode I named variables quite badly. Actually, now thinking about it, I think I used quite terrible names for my variables. But it doesn't matter. We will fix it as we go. So this is a second example, and I will actually comment it out as an example of watchdog reset. And now let's do a windowed mode, which we implemented, and let's see if it works as expected, as I understood it, and also therefore create a nice example. We do not need to test if our controller will be reset. We are testing this by setting it up simply in a first example, which is, this is the second example. Example 2. And this will be example 3. Example 3. Windowed watchdog reset if none in window. So how should this work? So we provide, for example, minimum duration for watchdog as 2 microseconds. 2 milliseconds rather. No, 2 is too small. Let's say we provide like 1000 again. Why not? And then we say that our window should be 500. So the watchdog is expected to be called between 500 and 1000. And if it's called earlier, this should be an error. So with this logic applied, so we turn on LED, do a 2-second delay to prove that the LED is on and we are not reset. Then we enable our windowed mode. Watchdog windowed, and let's say 1000 here and 500 here. Remove this, and now in this code we reset after 200 milliseconds, which should actually cause a MCU reset because 200 milliseconds is too fast. So let's see if our microcontroller will be reset again. So if we will see the D2 blinking. roughly every 2.5 seconds. So let's see. So it's flash. And let's make sure that I understood how this watchdog is supposed to work. So let's try it. 2 seconds first, then it didn't work. What? Hold on a second. Again, how is the window? Actually, let's first check if we have any errors. Maybe I provided something incorrectly or implemented something incorrectly. Oh, we have an error. Oh, I think I'm a dumbass. I think I am a dumbass. Oh, of course. Because this value should be smaller than this value always. So it is, if it is bigger, this is an error. And so this will be minimum target duration, and this will be minimum reset duration. I think this should make much more sense. Like this, and like that, and now it should work. So if minimum reset duration is bigger than minimum target duration, we are in trouble. Let's debug and see if it works. Let's run it. So 2 seconds and reset. Perfect. So 2 seconds resets, 2 seconds reset. So it works now. Okay. My understanding was correct. So if we call our reset too fast, problem happens. And now let's make sure that we implement the properly functioning example. So we will have example 4. So this will be example 4. Window should reset if not reset if in window. And in this example, let's say we will update our LED every 600 milliseconds, and this should just work. So our LED should be just blinking. This is actually quite an interesting feature. So let's run it. And we should see LED blinking. Yes, it works. Ha 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 ha, it works. Very, very, very nice. So all of it works. Let's make sure that the code is clean. This comment is important. This comment is important. This is unknown for now, but I will do it off stream because it's quite a long investigation for very limited return. Function. Okay, and I will need to provide a proper to-do, write proper function descriptions for function description. And I will have description. And I will have the same one for the second function. Because they both are, it is important to know how to use them, both. But they are properly functioning and are nicely implemented, and that's it. It is our implementation of independent watchdog, and we have also a second watchdog, so let's implement it as well. Right. Anything else? Anything else? No, I don't think so. So let's read our second watchdog. And our second watchdog is the system window watchdog. So introduction, the system window watchdog is used to detect an occurrence of a software fault, usually generated by an external interference or by an unforeseen logical conditions, which causes the application program to abandon its normal sequence. Have no idea what it means. The watchdog circuit generates an MCU reset on expiry of a program timer period unless the program refreshes the context of the down counter before the T6 bit is cleared. MCU reset is also generated if the 7-bit down counter value is refreshed before the down counter reaches the window register value. This implies that the counter must be refreshed in a limited window. So this is basically this, but different. But the VVDG clock is prescaled from the ABB clock and has a configurable time window that can be programmed to detect abnormally late or early application behavior. It is best used for application requiring the watchdog to react within an accurate timing window. Oh, I see. So giving that this has its own RC clock, it is not very accurate because RC clocks are not very accurate and the clock is very slow. And this is clocked from the APB, so this can provide like microseconds delays, I would assume. And this cannot. This can only work with milliseconds. Oops. So in this case, that actually kind of makes sense. Okay. So this then makes a lot of sense to implement it and use it only when it's needed. So programmable free running down counter, conditional reset, reset when down counter values become lower than okay. And reset if watchdog activated if the down counter is reloaded outside the window. Okay. Early wake up interrupt triggered if enabled and watchdog activated when the down counter is equal to this. Not sure what it means. I would imagine that this is a low power mode related things, but let's read. If the watchdog is activated, the VDGA bit is set in the register, and when the 7-bit counter is decremented from this to that. Oh, wait a second. What is 40? 64, okay. It indicates a reset. The counter while the counter is greater than the value stored in the window register, then reset is generated. If the software reloads the counter while the counter is greater than the value stored in the window register, the value higher. Okay, sure. Wait, what? No, correct. The same behavior as here. The application program must write the CR register at regular intervals during normal operation to prevent MCU reset. This operation can take place only when the counter values is lower than or equal to the window register value and higher than this. The value to be stored in CR register must be between this and this. Wait, what? Okay, this is actually confusing. Enabling the watchdog when the user option as we select software window watchdog. The watchdog is always disabled after a reset. So this is option bytes. It is enabled by saying this pin bit in this register. Okay, so let's start implementing. So let's say this is for our independent watchdog and this will be for our window watchdog. So pif setup we watchdog. And let's say it as a void for now. We will change it later, of course. So what this documentation says is that at some point we need to do VDG CR or equal to if it's enabled by setting this bit. Okay, it will be VDG CR VDGA. So this enable windowed watchdog. What else should happen here? Something happens here. So let's keep reading. Okay, so the down counter is free running counter down even if the watchdog is disabled. Okay. Once the watchdog is enabled, the T6 bit must be set to prevent generating an immediate reset. Okay, so we need to write it here before we enable the timer then. The fifth to zeros bit contains a number of increments that represent the time delay before the watchdog produces a reset. Timing varies between a minimum and maximum value. Due to unknown status of the prescaler when writing to the CR register, contains the high limit of the window to prevent a reset. The down counter must be reloaded. But this is way more confusing than the first watchdog. What? Contains the high limit of the window. This is okay. Must be reloaded when its value is lower than or equal to the window register value and greater than this. Sure. How to program the watchdog timer. Oof. As a formula is calculated, timeout value is given by time PCLK. Okay, it's after the prescaler. Was it's APB clock. This is a confusing name. Then multiplied by this, multiplied by okay. Why multiplied and not divided though? What the hell? The current time is. Oh, so okay. So this is a watchdog time. What? Still. Why do we multiply? As an example, if APB frequency is 48 megahertz, set to 3 and set to 31. And here we divide. What? 1 divided by what are you even calculating, brother? What is that? Why do we divide here? Oh, it's period. Wait a second. And period is 1 divided by frequency. But why we have only 3 zeros here? Shouldn't we be having 6 zeros here? Oh, it's in milliseconds. Okay. Oh, okay. Oh, this is hella confusing. Holy cow. So in milliseconds, sure. So that's when division by 1000 comes from. Okay. Then this makes sense. This part makes sense. This part makes sense as it is a setup. This part is a setup. And given that this is a period, we see, and this is also a setup. Okay. Refer to the datasheet for the minimum and maximum values of this. Okay, let's refer to the datasheet. Let's do this actually. So this is current consumption, min, max, timeout. So have a separate prescaler, sure. Max timeout value and min timeout value. So from 200 microseconds to 12 milliseconds. Okay. Guaranteed by design. Sure. This is kind of confusing, but whatever. The independent watchdog was so nice to work with, and this watchdog is an S. Complete S. So when debug enters debug mode, so yes, sure, we will need to do the same here. So that the watchdog is not triggered inside the stop, debug stop. So let's see, it should be VV, watchdog stop. Make sure that windowed watchdog is stop during the debug stop. Sure. Okay, interrupt. The early wake up interrupt can be used if specific safety operations or data logging must be performed before the reset is generated. Oh, actually, this is very nice. This is very nice and very useful. Okay. Okay, so this is very useful. And we need a flag for this. Sure. Oh, data logging must be performed to enable the early wake up. Okay, let's do it. So it will be vvdg cr or equals to bit to 0. So we need to set it to 0. So we will need to do it like this, and we will need to do it like that. vvdg sr. Oh, so there is a single bit. So we need to set this bit to 0, which is done like this by reversing the mask. And we also need to write a bit in another register. So vvdg asfr or equals to the mask. So it will be vvdg cfr wi. So this enable EVI, which is early wake up. Oh my god. Wake up, up, interrupt. But I need to close it because it will require an interrupt handler. So we also will need to provide a weak, and we will need to go and look how the interrupt handler is named, which we do in our startup file, I believe. And our startup file is stored in here. So let's see our interrupt names. vvdg IRQ handler, sure. So we will provide it as weak void, and it will, oh no, actually let's do it all the time, because why the hell not? Given that we have this, we will just do nothing here. Just do nothing if you don't use it. Okay, this is actually perfect. So enable it anytime the watchdog is enabled. Just don't use anything unless a user implements it in the actual device firmware. Okay, then when the down counter reaches value 40, a watchdog interrupt is generated, and the corresponding interrupt service routine can be used to trigger specific actions such as communication or data logging before resetting the device. Sure. If some application, the EWI interrupt can be used to manage software system check and or system recovery graceful degradation. Okay, of course. If we are, sorry, for example, spinning a motor, we can use this to speed down the motor to a halt before allowing our device to reset, or to disable the drivers, like to do a lot of important things, which we actually cannot do here at all. So this is a big advantage of this then, because this watchdog doesn't help us in this situation at all. And this is actually a very big point, if you think about it. Because this just resets everything. And for example, if our motor controller controls a robotic arm that, for example, got stuck lifting some load and it's reset, then everything will go down and like things may explode. Okay. So this is very useful then. Okay. Sure, the watchdog interrupt is cleared by writing 0 to the if. Okay, so we need to not do nope, we need to clear the interrupt flag. And this will be done cr equals, because clears are always write operations, not else. Like this, no, like vvdg sr, and this flag that documentation wants us to use. Then when the watchdog interrupt cannot be served, for example, due to a system lock in a high priority task, the watchdog reset is eventually generated. Eventually, so they do not explain how eventually. Okay, so it will happen at some point, just trust us, brother. So window watchdog registers, sure. So we read all of it. It was very short and very confusing. So let's start figuring out how to actually practically use it. because also it didn't tell us much about how to set it up properly. Oh, and we also need to enable the clock for this. So let's go and look for the clock we need to enable. So RCC registers, close, and let's go and see what clocks do we have available. And where are our clocks enables? Our clock enables are not here, and not here, and not here. Those are resets. Reset, enable. So not here, not here, not here, here. So we need to do an RCC dot RCC as register dot APB1ENR 1, and we need to enable the clock for our watchdog. So it will be RCC APB1 ENR 1 VVD enable. And we must always use double nopes here. No question asked. And after this, we can start doing the setups. Oops. And our setups will look how exactly? So this is to enable the watchdog, and this is those bit contains the value of the watchdog counter decremented every reset is produced when this value is 40. And the maximum value of this is like how many actual cycles do we have? We have 6 of them. Wait, what? We have 7 of them. But 40 in hex is 7. Hold on a second. What? The reset is produced when it is determined from 0 to 1. C6 becomes cleared. Oh, I'm a dumbass. Okay, so we have option from this value to all of it being ones. I'm such a stupid person, sure. So we have an option from 1, which is at 40. So let's write it down. So our options for T field are 40, 1 cycle is set, 2, which is 040, 204F. No, it will be not 4. It will be 7F, which is here 64, and here will be 187. And this will mean 63, 64 cycles reset. So we can do from 1 cycle to 64 cycles. Oh, this is so confusing. Okay. Sure, we need to somehow determine these values. But we can, sure we can. And then here, configuration register, so time base was, okay, so we can divide from 1 to up to 128. So we need to at least add our definitions to our enhancement, CMC's enhancement, to be able to support this functionality. So let's go here. And let's create another section, which will be called Window Watchdog Enhancement. And here we will define a few of them. Define, oh my god, define VDG, CFR. It will be VDGTB, correct, divider, by 1. Let's start filling them in. I have no idea why STM doesn't provide them by default, but whatever. It will be by 4, by 8, by 16, by 32, by 64, by 128. This is unnecessary. And now let's fill these fields and make sure we are correct. So this will be 1. This will be 1 here. This will be 3. This will be 4. Oops. 4, 5, 6, and 7. Sure. 6 and 7. Okay, sure. If it's an early wake up interrupt enable, sure. And the V field is window value. This bit contains a window value to be compared with the down counter. Sure, we should also set up those. So let's go to our implementation. And let's say so. This can be enabled here. Right away, we know this. We need to somehow determine the value we will put into the T register, which is CR. It will be. So how should we do it? We should, and actually we can just write. We can write question mark, determine how to select value here. And we also need to do similar thing with G, CFR equals to question mark. And the question mark will be, actually, let's set it up later so that we can use just writes. Because otherwise we will need to use not a write here. And this will be determine how to select the value, select T value here. Okay. And this register is just a status register, early wake up interrupt flag that we are resetting here. Sure. And we have nothing else. So those are 2 questions we need to answer while we set up. And how do we answer them? Okay. So let's start doing some math. Let's do some math. And we need to do math online because we will need to use a multi-formula. And where is my Wolfram Mathematica? No, thank you. So let's say we start with 150 megahertz. So 1 more 0. We have 150 megahertz and we divide always by 496. We always do this. And our answer is not even an integer value. Holy cow. Sure. Okay. That will be rough. So it is not even an integer value, and this is only a first prescaler out of multiple. So let's put it to the side and let's get back to our datasheet, which is where I lost it. Oh, it is also here. So let's actually switch them up. So now, where is our formula? Oh, we also divide this by 1,000. Hold on a second. No. Oh, fuck me. Oh. Timing. We would like to understand how many milliseconds will be taking for us to do things. So it actually will be 1 divided by this number without 3 last zeros, according to this formula, multiplied by this value, which is not an integer. it is an integer in the microseconds. No, it isn't. Actually, it is not. And then we multiply by 2 in the power of whatever we select, and we can select up to 128. Holy cow. And then we multiply also by from 1 up to 64. Let's say 32. Is this even a Wolfram function? It is actually very interesting. Was. Holy cow, this is long. What is happening? Okay. No, wait, it doesn't make any sense. The time base of the prescaler can be modified as follows. Makes no sense. 2 in the power of 3. Oh, I see. So they use this number, not this number. Okay, okay, this makes sense. So it is not 2 power of 128, just 128. Sure. Sure, that does make sense, actually. And this will give us value in what units? In milliseconds. Okay. So how do we automate it? How do we automate it? Because what we have to select are 2 values. We need to select this value and this value. And what is the best way to select them? Oh, actually, no. Actually, I have an algorithm to do it. I actually know how to do it. It's very easy. But, so what is the idea here? We need to specify the time the same way we did it in... Let's move it back here. Okay, let me keep thinking. So we need to specify the minimum target duration. And also we need to specify both the parameters as we did here. Like that. Oops. Like that. So this makes sense for now. And now that we know this value we would like to achieve, we can start the calculation. And this is in microseconds. So let's say the user... Wait, it is in microseconds? No, it will be in milliseconds. I'm a liar. It will be in milliseconds given the new interface in these functions. But this function can actually work with microseconds because I have no idea what I'm doing for now. Microseconds, I would imagine. Why is it so hard? Microsecond and microsecond. Sure. Like this. This is a function, so should have a return value. What? Sure. Okay, this is just awful. Now it's less awful. Okay, so now that we know this value, what do we do with this? We do some shenanigans. So let me think. First, we of course, we need to calculate our const. VVDD, VVDG, clock divider. No, clock frequency. It will be base frequency. No, it will be calculation frequency, and it will be. We need to include our clocking here to make it work. No, not clocking, but include device definitions. So now with device definitions enabled, we will have, it is an APB bus, right? Let's actually open Cube MX and let's make sure that I am not tripping STM32 Cube MX. A moment. Let's make sure that I'm not tripping over myself. And let's say MCU selector. Okay, sure. One CPU. Now let's go to our clock configurations and let's see. Do we have anything that's called watchdog? We don't. So we just need to. So this was useful, very useless rather. So it sits on an APB1 bus, and APB1 bus has frequency. We know. So and the frequency will be. Actually, I think I closed it too early. It wasn't useful in a way I supposed it would be, but it was useful in another way. Okay, but let me open my clock configurations. So device definitions. Okay, so we have AGB prescalers and APB prescalers. And this will be then CPU clock frequency divided by AHB prescaler divided by APB prescaler, 1 bus prescaler. And we also need to divide this by 1,000. That's kind of confusing, but it makes a lot of sense, actually. And we also need to divide this by 1,000. Let's open the CubeMX again and check if I'm correct, actually. Actually, let's not be lazy and let's just check it. I actually have a project that can be used, I guess. Okay, clocks. So we have this clock, which is the same as our CPU clock. We divide by HB. We have our H clock. Okay, sure. And only timers are here. Right? So do I have defines for, let's say, H clock? HCLK? No. And do I have a define for sys clock? Sys clock? Sys CLK? Nope. And then we works with what we have, which is this. And this provides us with correct, always correct, no matter how we decide our timers, this value. This value. It will be always correct. It will be a time on the APB bus, APB1 bus with like in not kilohertz rather, given that we divide by 1000. So now, given that we have this value, what we need to figure out is to actually how we select these two values. So this value and this value. And to do this, so we have duration. Let's say our duration that we want to achieve. Let's say our minimum target duration is equals to 100,000, which is 100 milliseconds. So we want to achieve it. So we want the product of 2 in the power of 1 register, reg 1, multiplied by reg 2, being equals to what exactly? So what exactly? Oh, rough. Yes, exactly. Correct. So we just need to move everything to this side. So this duration multiplied by this value, actually multiplied, now divided, and then divide by 496. Yes, and this is a period. So then it will be a uint32 target product, okay, whatever. To do rename. So is this correct? Let's actually just run it and test it if this will give us the value expect. It will be just much faster than me making sure that everything works in my head first. So let's go to our bring up example. Wait a second, what is this? Bring up run error state. Is it used anywhere? One moment, I got distracted. It's never used anywhere, so we might as well just remove these files. I don't remember what the idea was, but they are not useful. So here we are in our example. Let's remove this. Now we are guaranteed to need to set up clocks. System clock. And then we set up our div setup the watchdog. And let's say we want milliseconds to use seconds. We want 100 milliseconds there. And the minimum time we would like to have is actually, let's say, so it should be reset up to 100 milliseconds, but it can be reset, let's say, I actually have no idea if those values make any sense for now. Because actually the maximum value we can achieve at any time is 128. We have a very, very defined limit, not standard, scientific. And our defined limit is 128, correct? 128. That is multiplied by 64. This is the absolute maximum we can have. So if our value is bigger than that, our target value, then we are in trouble. And this limits us quite significantly. This limits us very, very significantly. So if this is maximum, if this is maximum, then with 150 megahertz, I'm not sure that 100 microseconds is even achievable. 100 milliseconds is even achievable. So let's calculate it. Can I open another calculator so that I can have this value in place? I can. More calculators. Actually, let's go and open Wolfram. So let's say, oh, I can actually check my formula even without running anything. Here. So this will give me 150k, which is this, and I multiply by the target, which I'd say, oh, why is this so hard? In milliseconds. So the target should be in milliseconds then. Oh, fuck me. Okay, let's say that this value is in milliseconds. Then we multiply this by 100, and then we divide by 496. And what is the integer equivalent? 3662, which is actually supposed to be within our limits, so we can achieve it technically. Technically, we can achieve it. Right? Right or wrong? But why did I use milliseconds there? It makes absolutely zero sense to me. Like, it kind of not, but it kind of does. The formula to calculate the time at value is given by milliseconds. So milliseconds are the output. So this is correct. So we need to provide milliseconds target. So our target is in milliseconds, and we specified 100. So we can achieve it. We can definitely achieve it. Okay. Oof. Tough. Very tough. Very, very tough. Okay. So the target is achieved. And let's say if target, and I also wrote target wrong, target product is bigger than 128. What do we do then? What do we do then? Let me remember my algorithm. So let me think. My algorithm was to actually use the highest value to divide the value we have. But now I'm not sure if it's working actually. Oh my god, my head hurts. Let me open a sketchbook. Scully drew the beauty of bare metal development. So let's say, for example, that we have 2000 as our target, and we can select any value up to 128 in one register and any value up to 64 in another register. So my idea was that I need to divide by 128, and this will give us roughly 8, probably a bit less than 8. Let's see. Oh, 15, 8 by 2. Okay, so this gives us 15 integer. And then we'll use here this value plus 1. So this value will be 16. And then our resulting multiplication will bring us to what value? It will be 128 multiplied by 16, 148. So the error will be 48 bits, which is kind of significant. And why did I believe that the error would be lower? Oh, I know why. I know why. Because this algorithm works very well when we have much higher limits. If we, let's say, wait, does it work well? Let's say we could have taken here up to 1000. Let's say not 1000 because 1000 is too nice of a value. Let's say like 900. So if we were to get here 900, we will get 2. We will divide by 3. Oh, hold on a second. What? Fuck. We would divide by 3. We would divide by 2. We will get 3. And then we divide by 3. This value divided by 3. Oh, and then we could have updated this value as well. But we cannot because we only have powers of 2. So this sucks then. I know that I'm talking to myself, just bear with me. If you have questions, I can answer. Because this algorithm is very nice. It allows us to find a product of 2 numbers, x1 multiplied by x2, that is very close to this number in like 3 mass operations, 3 operations. It will have error, but the error will be low. But the requirement for this algorithm is for both of those values being stuck to a limit and us being able to use any value up to this limit. But this is not the case because we can only use 12, 4, 8, etc. And given that this algorithm doesn't work as I expect it to, then what? Then what? We will have 3 cases, 3 separate ones. Should we actually use the smallest possible value we can use? Oh, actually, let's switch it up then. Let's divide by 64 first. So what we will have? So it will require a loop, but loop is better than nothing. A loop is better than a more complicated algorithm. So when we divide, for example, 2000 by 64, we get 31. So let's select 32 as our number. So we need to get 32 here, and we are lucky because we have 32 here directly. So we just get this value, and we have the same error because this value is just terrible value to select from. So let's say our value is 2173 for a better example. And let's do calculations again. So 2173 will be divided by 64, which is our maximum allowed value. So we get 33 integer. So we get 34 as our setup, as the value we need to get here, but we cannot. We get the smallest value we can get, or actually the biggest value we can get. And the biggest value after this will be 64. Any value bigger than this, which is the power of 2, which is 64. So now we go back and recalculate. We get our number, and we divide by 64. And we get, oh, right. So these are the selection then. No, it's terrible because number switched. Let's select different value. Let's go for like 4, 3, 3, 1, 7, 3, 1. Again, we go again. This is breaking my calculations. So 4731 divided by 64 is 73 integer. 73 integer. So, and we need 2 plus 1, so it's 74 integer. So what we get is 74, but we cannot get 74, and the closest one that's bigger than this is 128. So we will have to use 128 in this example. And when we divide this by 128, we get 36.9, which is plus 1 in integer will be 37. And we get our result as 128 multiplied by 37, which is 4736, which is very close. Holy cow, this is so good. This algorithm is so good. We are so close. We are just 5 bits away. I like this. This is a complete mess, but this algorithm is very smart. Now let's implement it then. Right. Right? I think so, yes. I think this algorithm will have 3 different parts, depending on where we are. Or maybe 2 parts, but it will be a very nice implementation. So here, by doing this, and this will be in milliseconds, because otherwise this algorithm doesn't work. Let's also rename this. So this is value in milliseconds. We multiply, let's say it's 100 here. Well, technically this algorithm still works, but we will need to use floating mass, and I don't want to do this. At least yet. So what we get is our product. We divide by 496, and we get 3662. Sure, perfect. And then if the value is higher than 128, we apply our algorithm. So we will have here else. And our algorithm will be to see initial, will be uint32, initial diff, and this will be our target product divided by 64, because 64 is the maximum we can set in our registers that can that can change by single bit. So our initial diff will give us something, and let's say we work with our particular example, which is 3662. So let's use our calculator and go through this. So 3662, we will divide by 64, which will give us 57. It will give us 57. And we do +1. Because we need to do a +1. So now we need to find a closest power of 2 that is bigger than this value. And how will we do this? We will have to have a loop, I would imagine. Maybe there is a smarter way to do it, but I don't know it. So let's do a loop. For uint32 ei equals, let's start from 0. So should we go up or go down? Actually doesn't matter. It doesn't matter at all because we only have like 7 iterations of this loop. It doesn't matter at all. So -7, or rather less than this value. It will be more obvious to the reader who understands what's going on. And here, so current actually uint32 t divisor power equals to 0, and this will be empty, and this will be divisor power is less than this, and divisor power +1, and our actually uint32 t current divisor equals 1 left shifted by our divisor power, which is just 2 in the power of something. It's absolutely the same thing. So it's just 2 in the power of divisor. Okay, and now what do we do with this? if we also need to add check here if target product is bigger than 128 multiplied by 64. It is an error. VVDG registers cannot support such a long duration. So let's log this error as 3341 for whatever reason. Let's make sure at some point in time I will do a proper error code. Add a proper error code here. And we will not return. Instead, we will just apply the target product. Actually, we will just apply the maximum values. So, and the maximum values that we apply, so there will be else then, and this will be run in the else loop, not loop, but in the else branch. And here we will just select what? So let's say uint32 t. Oh, so let's actually just do what we need to do. It will be VVDG, VVDG, CR, and there will be t equals to whatever is the value it's supposed to have. It will be 64, which is the maximum value we can set there. Yes, and we will also have uint32t, VVDG, CR, not CR, it was a different register. Let me see. Oh, this is going to be so nice actually. CFR, and this will be W, and this will be 128. No, it will be OA. This is a power. So this is a power, and the power is 7. So this is the maximum value. And if we have an error, we save defaults and we use defaults here. So here we can already implement it directly. No. Hold on a second. Oh, I'm a dumbass, right? This is, we are getting VGTB here. It will be with GTB, with EGB, sure. Like this one. And we also will have to have a uint32t, VVDG, CFRW. And the default value for this will be the maximum value for this. And the maximum value for this is everything is 1, which is 7F. Oof, rough. But we're getting there, we're getting close. Bare metal development. So, and here we can actually start writing it all into registers. So let's say in the CR, we will put R VVDG, CRT, and to be stylistically correct, let's do it like this. T position. So this is a stylistically accurate way to do it. And this will be just equals because we can allow it to do it. And in the SFR, we can do the same for now. Yes, we can just do the same. So we will have our VVDG CFR VDGTB. It will be shifted to VVDG CFR VDGTB. Pause. And we will at the same time write our VVDG CFRW to the VVDG. So let's make it cleaner. VVDG CFR W position. So this is the way to write it. This is the way to write it down, and we need to just determine the values like this. And this is very nice. Everything here is already very nice. We just need to finish all our algorithm. So here, if we happen to jump into this branch, what happens? What will happen? We just log error and execute this part of the code with the default values we set up here. And here, so if target is higher than 128, here will be else if target product is higher than 64. And here we will just set this to 0 and this to whatever the target is. This is the easiest part. And now we have two hard parts. Actually, I don't think we have a hard part. We will just do this to be equals to 1, and this will be equals to target product divided by 2. And here, if VDG RT multiplied by 2 is not equals to target product, we will need to bump this value by 1. Okay, my head actually really hurts from thinking. Okay, and now the hardest part. So here we do nothing. We increase the divisor from 0, so it's 1 as in power of this, which is correct. And if the current divisor, okay, I already forgot the algorithm while implementing everything else. What was our idea? So we have 57 here, and we need to find the highest value that is higher than this value. Sure. If current divisor is bigger than initial diff, we break. So we found a setting for, actually, why do I need to write it down? I can just use this and equals to this. Right, 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 sure, and break. So this is it very nicely. And now at this point, we need to do a back calculation. And to do a back calculation, we will do what? We will give another variable. So this can be const. This algorithm will work always because this condition exists. Okay. So we will not have any edge cases. And here it's correction diff, and correction diff will be target product. divided by actually, hold on a second. I think I need to do an additional check here. To do it, additional check in case the division is integer, so without a reminder. And in this case, we will not need to do +1. Let's just implement it. Why do I need to do it? It's so easy. If our initial div multiplied by target product, no, by 64 is equals to target product. Actually, if not equals, we just +1. Like this. Does it make sense? Let's test our algorithm on the value that will have this as the case. So let's say our value is actually, let's finish the algorithm and then we will have 4 different passes that the algorithm can go, and we will just test all of them. Actually, this is a very nice function to be put into a separate function and to be put into a proper unit test. It's a very unit testable function. And we can actually maybe do this, because why not? It's actually a very unit testable function. But maybe I will not, because it can be tested without unit tests and just left there to live forever. Okay, so at this point we need correction, and this is target product divided by the current divisor. And yes, so let's do current divisor here, and let's do it here because we will need to reuse it. And we divide by this. And in our case, with our example, it was 57, so this should give us 64 for our particular example. And in this case, we divide the target product by 64. So what will it be for our 3662? We divide by 64. It will give us 57. We need to do absolutely the same check. So if correction div multiplied by current divisor are not equal to target product, we do +1. Plus equals 1. Okay, and at this point we have what? We have 58. At this point we have 58. And these are our values, 58 and 64. And they should give us what exactly? And we save this here. Equals to correction div. So let's say 58 multiplied by 64 will give us 3712. So it gives us 3712 with our initial value being 3662. Was? Are we off by more than 60 to 64? If we divide it, hold on a second. 3662 divided by 64. Yes, so this is the closest we can get to still be higher than the value, because our algorithm assumes that we would like to be higher in duration. So this is correct value, and this is the closest we can get, because otherwise we can get 128, but with 128 we will just not get the value. And even though the error is pretty significant, so we are slightly longer, like by a significant margin, it will be like 38 plus 12, it will be by 50. So we are off by 50, but this is the best we can get with what we have. Hello, multiplexer, how are you doing? Oof. So I think the algorithm is working. So now we need to just edge case it. Edge case it. So this should be tested. This should be tested. This should be tested in 4 different configurations. When we have none of those triggering, when we have one of those triggering, we have another of those triggering, and when we have both of those triggering. So we have 6 test conditions we have to test. And this also for this duration. We also have a similar problem with this duration. I'm good. I just joined. Motor control sounds fun. Yeah, but today we don't motor control. We implement the safeguards for the motor control, which are watchdogs. And my brain is melting out of my ear. And you are still not following. I see you. I see you. So how do we test it? And we also need this value. And how do we obtain this value? How do we use it exactly? How do we use it? Oh, there are 2 test cases for this value. Watchdogs are... How much do we know about microcontrollers? It's for me to explain it in the best way I can for your knowledge level. So you still cannot follow me. That's interesting. That's interesting. I have basic electronics knowledge, not much motor control, mostly sensors though. Okay, so you know what microcontroller is and how it works. So watchdog timer is a timer that you start in software and you need to reset periodically. So you need to reset it, for example, every 10 milliseconds. And if you do not reset it in software, it will reset your microcontroller. And the idea here is that if you can reset it with a given period, the firmware is healthy. So everything works as expected. And if you cannot reset it in time, it means that something in your firmware is stuck and you need to reset your microcontroller. So these are what watchdogs are. I hope it's a clean enough explanation. Okay, perfect. And we implemented today an independent watchdog, and it was very easy to do, given that it has separate clock, which is nicely divisible. And now we are dying inside to implement a nice way to work with windowed watchdog, which is slightly different but the same, but it is a pain in the ass to implement. So what were we saying? We were saying that we already implemented everything for our main value, and we also need to somehow use this value. And how we will decide this? Oh, this is so rough, because this value also depends on this and on that. So we can only approximate it very roughly. So first of all, if this value is bigger than this value, we log error. Let's say it will be 7 for whatever. Add proper error code. And we also set this value, which is actually should be 64. Oh, I know an error. I know an error. This value should be -1. I assume watchdogs are mostly something you use if you don't use RTOS and instead schedule everything manually in the code. Why though? They are useful for RTOS as well, because if your RTOS tasks are, like, for example, stuck, if some task just doesn't want to release the yield the thread for whatever reason, for example, it waits in the queue for the target that never comes because your sensor just got unplugged, and it will loop forever. Without a watchdog, you will not, like, your microcontroller will not reset. And with a watchdog, if such situation happens, no matter if you use RTOS or not, your microcontroller will reset. So it's still useful, very useful. And here, no, this is actually incorrect. We need to do 0.400 plus this. This is how it's supposed to be done. Oh, okay, I see that's neat. I can't believe I had not heard about watchdog until now. Sure, that's not a big deal. Watchdogs are useful, but they are not given for people who are starting microcontrollers, even though they are not very hard to set up, unless you do it manually like me. But yes, they are very useful when you know how to use them. And I just decided to implement them. Bare metal, of course. Only hardcore here. So that I can use them effectively in my code, in my firmware. And here should be the same thing exactly, just with a different variable. CFRW. And a bracket. No bracket. No, a bracket here. A bare metal implementation gives a special kind of satisfaction. It does, it does. When you finish it, it does, and I'm very close to finishing it. And I think I used a very nice algorithm to do it. So I'm kind of happy with myself. I just need to test it. I just need to test edge cases. Okay, so here we log error, and we set this to be the same as this. Okay. And in the other cases, how do we decide which value it will be? We cannot change this divisor anymore. So let's say you insert it to divisor divisor v will be equal to our target product, which should still be available. Yes, very nice. Divided by whatever we decided as our 1 power of this. And if, how are we doing? Oh, hello. Hello, Zoe Hart 644. Look, you are to focus in this. This is my Discord. I got something to show you. I see. All right, of course. Sure. Something to show me, of course. So, getting back to the thought I had. Getting back to the thought I had, it is supposed to be what? In our particular case, let's say we set this to 100. Bots are getting more and more sophisticated these days. Yeah, they are. They are. I actually had quite a few bots that were like asking how I'm doing and stuff. And then they were actually listening to answers as well and replying to them, but they were like getting banned in an hour. So let me actually just ban this person. Let me actually just ban this person. Zoe my S. Okay, so in our example, let's say we set our targets here as 100. This is what we were calculating for. And our second target will be, let's say, 40. In this case, if our second target is 40, oh no, we have to have a new target. So we will have target product W, and this will be equals to the same thing, but with different flavor. So it will be reset duration like this. And then we use this target product and we divide it by this. Make sure that operations are in correct order. And let's say we have 40. So what we will achieve, we have 40 multiplied by 100, 50K, and divide by 496. So we have an integer value of also, I think I have another error. Let me see. Because unless oh, fuck me. This is so mind exploding. So let's say we are expecting 1464 here, exactly for now. And let's say we already have 64 as our divider. So we take this number, divided by 64, and we achieve this number. So this is our divisor. This is what we get. So it's 24. And this number multiplied by this number not equal to this number, then we need to add 1 here, plus 1. Okay. Now it should work, but I have my doubts about these numbers. So let's figure out if we need to add 1 or not here. And how will we figure it out? We will just check the documentation, of course. So let's see. Back to formula. So our duration in milliseconds will be equals to, let's get our Wolfram open. So our target was 40 milliseconds that we want to achieve. So we are getting 40 here and divided by this number. So we get 1464. And this is what we need to achieve here. And if we achieve here less than this value, then this duration will be less. So we need to plus 1. Otherwise, our duration will be less than expected, which may hurt us. So we need to add it to 2 places. If target multiplied by 496 is not equal to this, we have to plus 1. Plus equals 1. So let's redo the calculation with our targets. So here we just get 100, for example. It's give us 3662, and it will give us 3663 at this point. And we go again. These are defaults. We make sure that the multiplication is, this value is smaller or equals actually. No, just smaller, just bigger. Correct, it is not. So we go into the else branch And in the else branch, we say if the target is higher, it is. So what we do is we produce an initial divider. We remove this part. So we divide our 3663 by 64. We get 57 at this part, and at this part we get 58 because we have 57 plus a remainder. This is implemented. So we go here and we run our algorithm. So we find the highest power of 2 that is bigger than this number, which is 64. This gives us 64, and we go here again. We take this value divided by 64, we get absolutely the same value, which is 57, just in this example. So here we get 57 again. And this will be bump again. So we get 58 here. And 58 by 57. No, 58 by 64 is 37212. So we get our closest value, closest possible value. This algorithm works nicely. And this gives us what? Now let's actually plug these numbers into our formula, and let's see if our duration is correct. So it's 3712. So let's plug it here. It will be 1, no. Yes. Yes. So 496. It will be multiplied by 64. It will be multiplied by 58. And it will be multiplied by, it will be divided by 150,000. Correct. And this will give us 101 millisecond, which is bigger than the value we specified, which is correct because we want a value bigger. So this algorithm works. Hooray. Now that means that the value, the implementation with the window works as well. And now let's test.
1999 just followed.
Oh, Bini 1999, thank you so much for following. How are you doing? I hope you are not a bot. My heart will not take it. So let's test the edge cases, and our edge cases will be when we have to divide by what exactly? Would be funny if it is a bot. Yes, would be very funny for you and very sad for me. A bot can follow, but I can't. Yes, true. Why can't you follow? Let me ban a person. Rest assured, I'm not a bot. Bots say things like this these days. So who knows, who knows? I don't know, I get an error in the console every time. Unfortunate. Okay, so let's test it. We need to have a situation in which, okay, let's test, in which we get the proper multiplication here. See, this is what a bot would say. Okay, yes, exactly. We had bots like this before, had it? Of course. How are we doing? How are we doing, Bini? What's up? So, because if you are not a bot, I can celebrate my first achievement in followers. 10 people, hooray! Let's go. Okay, so what is the edge case we are trying to catch here? And the edge case is, oof, this is rough. And the edge case will be when we have an exact division here. So we need a power of 64 a pure division by 64. So let's actually provide an example with 64 as an input. And if we use 64 as an input, what will our algorithm do? So let's get back the pieces. So target duration will be 64. So we get 64 multiplied by 150k and divide by 496 will give us 2343. Will give us 2343, which after this part will give us 2344. 2344 here. So we go into this part. This is not an error. We go into this part. It is higher. So we divide by 64. So 2344 divided by 64. Oh, so it is not an integer division. Hold on a second, but I need an integer division here. So I need something with this value. Okay. And this is the power of 2. It's power. It's 12th power. So let's actually try 250. Okay, we have 8 here. So we need to multiply by 8. So 64 by 8 is 512. So let's provide 512 as our target. So this should give us the expected edge case. 512 multiplied by 150,000, correct number of zeros, divide by 1496 gives us an integer value. Perfect. So we will get us. No, this is too much. What is happening? Why is my follower goal updated just now? What happens? No, I'm confused. Why is number so big? Oh, we cannot even provide this number, so we will never reach the edge case. But we will reach the edge case if our frequency is lower. So let's lower our frequency by the factor of what we saw, by the factor of 2. So let's say our frequency is 75,000 this time. It's still too much. We can divide it by 2 again. It will be 37,500 minus 0. Am I a dumbass? What is going on? Hold on a second. 150k divided by 275k divided by 2 again. It's correct, right? Follow on Chromium worked. Alas, it was at Twitch Firefox bug. Oh, I see, I see. Thank you for the follow. Multiplexer, 2 follows in a day. That's a respectable amount, I'd say. Thank you so much. Okay, and now I'm confused because I believe, oh, I need to divide by 2 multiple times, right? If I will put, oh no. But let's continue just for the sake of the example. So it will be 512 because we'll divide it by 2 again. And this division, I don't think I can make in my head. So let's just say that this number will be divided by 2 as well. What? Wait a second. Am I stupid? Am I stupid? Multiply by 2. And this number is bigger than 128 multiplied by 64, right? So is it like, is this error says to me that I cannot like literally achieve the situation when there will be an integer division without a reminder? It seems like I cannot. So no matter, or maybe I can, maybe I'm just stupid. So let's continue. We need to get here a value, we can definitely do it. I'm just stupid. For sure we can do it. So let's say we have 40K here. Like this, for example. This is already works. I'm just a stupid person. So let's say our frequency is 40K. Not 40K, but 40 megahertz, but it will be 40K in this formula. So in this case, we will get ourselves. So let's say for this example, this will be 40K. After the calculation, this calculation, we get 5,000 exactly. We check it, we do not add 1, we get 5,000 after this. And this 5,000 we put into here, and we divide by 64. And we divide by 64. Oh my god, and this is not a... Oof. Was. So, my god, how do I get this to work? Do I even, like, is an example like this exist? Even exist? It will just go smaller. And if I go here to 56 and I divide by 64, it's just getting smaller, so I need to go bigger. And if I go bigger, so this should probably be a power of 2 so that I can remove, and to be a power of 2, it should be 16. It will be 512. It can be 32, 64 actually even. And here it will be divided by 64, and it's right. Nice. We found an example. So in this example, again, 64 megahertz. And this is actually not such an unusual number to have as a frequency of your system clock. So we do the division, and at this point we have 8,000, which is very close to a limit, but not a limit. And this is also a very good test because we will test how close our limit is figured. So very nice. So we have 8,000 here. We go here. At this point, we divide by 64. We divide by 64. We get 125. We multiply, and we still get 125 after the multiplication because we don't have a reminder. And we go here, and we find a biggest power of, closest power of 2 that is bigger than this value, which is 128. So we get 128 out of this function. And now we go back here, and we divide it by 128 this time, and we get 74 because we have integer division. So 128 here. Here we get, no, 64, of course, 64. What? Oh no, this is what? Okay, let's keep going. 64 here. No, this is wrong. Did I make a mistake at some point? Oh, my god. If we divide by 128, 125. Should we divide by the power that is smaller? I'm confused. So if we divide by higher number, we should see. Am I bad at math? It's 62. Fuck me. I'm so stupid. Okay, this is 62. At this point, we get 63. I'm just stupid. I'm so tired. This is a hard implementation. I'm so sorry. Holy mental mess. Okay, 63 here. So we get, and this works, and our resulting value gets us 63 multiplied by 128. And we get this number, and we multiply by what does our datasheet, not reference manual, says, by 496, and we divide by 64, which we had as our value, and we get an integer value of 516 with 512 as our initial target, which is bigger, which is nice because we achieved what we wanted to achieve. And now let's say that in this example, so this example works, all the correction works correctly. So, okay, this edge case is tested. And I would imagine the second edge case works as well because the logic is the same. And now let's test, for example, that in this example, we had, let's say, 200 as a target for our window. Let's say 200 as a target for our window. And let's see. So if we have a 200 as a target, what we will get here, we calculate a new product. So 200 multiplied by 64,000 and divide by 496. Okay. And this value we divide by the 228, which we calculated already and we cannot change at this point. So we get 24.4. And if this is not equals, we plus 1. And plus 1 gives us 25. So we get 25 at this point. And we calculate, checks the frequency. I got my BSEE in the 80s when I was working with radios. Motors were just a source of noise. Now I play with 7400 and 400 chips in semi-retirements. Oh, this is nice. Hold on, 7400. Actually, I have no idea what it is actually. Where are they MCUs or? Oh, they are. Oh, so you play with such old components. Texas Instruments. No, but those are not microcontrollers. Those are logic gates. So you are making logic devices? And what do you mean by semi-retirement? Do you work half time? And have you been working with radios professionally? I would assume. But yes, motors now are like way less like noise generators than I would assume they were before. Both due to filtering and due to the way the motors are manufactured, with like better precision now. I would assume. Okay. So I was testing the values, and where is my Mathematica? Here. So let's get back to our formula. Was here. Okay, so we got 64,000. Now to test it, we multiply it by this value. No, we divide by this number. So 1 divided by this, multiplied by that, multiplied by this, and multiplied by 25. Will give us a delay duration of 2 and 4, which is correct. It is bigger than we specified. Wait a second, should it be bigger actually? Because this is a window at which if we are shorter than this, the reset will still be triggering. Actually, I think this is an error, and I think that the correct value, I heard the story a couple of times, hardware people transitioning to software because that is where the job are. I think it was the case before. Hold on a second. Did I get a donation? Holy cow, my first donation ever? Oh, but why do we not have a notification on stream? I would assume like one of you donated $3. I appreciate it a lot, and I also don't see a message. Wizards donation. Thank you so much for my stream. My first ever $3 made on streaming. I appreciate it a lot. I have no idea why the notification is not here. I will look at this after stream. But thank you so much. It was me. Message was, I'm just happy someone is streaming hardware on Twitch. Oh, thank you so much. I'm so sorry that notification doesn't work for whatever reason. Thank you so much for $3. I appreciate it a lot. This is kind of awkward. Thank you so much. So that was true about 1919. I actually think that this was true even 10 years ago. Like when I was finishing university, I'm 28 now. And when I was finishing university, like 6-7 years ago, like 8 years ago as well, there were a lot of people who were studying electronics and who were thinking like electronics just doesn't pay as well. And they want to switch to the software. And they were effectively switching to software. But now the electronics pays quite well if you know how to do it. And electronics, like terribly automated by AI. I think AI will never be able to automate electronics design properly. Because like my tries to do any electronics with AI were just completely horrible. Like they were awful. So I would assume that many people now who were studying electronics but switched to software, like are thinking maybe I should have keep doing the electronics. I would assume that this is the case. So at least this was like 8 years ago when I was studying. Yes, back to what we were thinking, and I was thinking that this is an error because I would assume that in this case, the window should be smaller. So we actually must not do this check at all. So this will be the correct implementation because we want this. Let's actually add a comment. We want this window to be exact or smaller than the target. Oh, you're younger than my children. I have a daughter with a master's in civil construction engineering. Yeah. Given that you were getting your degree at 80s and now it's like 26. So like it was 40 years ago. So you are about like 60, 65, I would assume. Are you from US, Bini? I think the defense and space recently increased headcounts for EE, for drone satellites, but where I live, software has still eaten the world. And when do you live, multiplexer? But yes, I actually agree, because with drones and stuff, there definitely quite a high demand for electrical engineers, like all over the world, actually. So this is a very nice time to learn electrical engineering, not in Europe. I see so somewhere like in Denmark, Norway, somewhere there. Oh, especially if you live in somewhere like Poland or I forgot actually the name of the country. One moment. Finland. I remembered. If you live somewhere there, I would assume, or like Estonia, Latvia, Litva. I would assume that these countries invest quite a lot in the defense now, especially like with all the events. 62 in US. Cool. Very cool. Thank you for watching me. I appreciate it a lot. And I'm happy that you are enjoying my struggles with this implementation. So this comment is done, and now let's test it on the actual hardware. So let's write a test for this. Let's write a test in our bring up 0. And okay. We set up clock, and we set up our beef setup watchdog V. EU in general is putting crazy money in defense now, but yeah, Scandinavia doubled it. So true, very true. My first job was with the US Air Force. Oh, in 80s, I think were they like developing F-15 or something back there? I think it was like a peak job to do back in 80s. You probably had like crazy experience, and you said you were working with radios, so you probably were working with radios for avionics. Sounds actually quite a cool experience to have. So we set up this, and let's set our target as okay, 100, because we saw that we cannot do much more than this. And let's put our target as our second target as 100 as well, because we don't want to use a window for now. Oh, so I actually already had it here. So yes, these are correct, but let's use this here. No, but we need to use directly because we switched our inputs to milliseconds, not microseconds. So remove this and this. Yes, MCMP. Okay. Must have been a blast to work on all the top secret stuff. Yes, tell us more. Tell us more. It actually sounds quite interesting to hear stories about. If they are, of course, legal. Only legal stories are allowed. And here, let's add a loop. And what we will do in this loop, we will do actually, let's also set up our LEDs for test. Set up, let's turn one of them on. So GPIO LED 1 should be turned on. And here in the cycle, we will toggle it. So let's dummy delay USEC. It will be milliseconds to microseconds. And let's say we will have a delay of 200. And after this delay, we will force our LED down. We will turn it off. And this will never happen because our watchdog is supposed to be resetting the microcontroller. So let's test it. It was a lot of meetings, even then, but I would assume that it is fine for defense and like space and defense, aerospace and defense. But like many jobs these days can be like described as a lot of meetings. But I would assume they were productive meetings, not like modern meetings. So let's flash it. We have an error, sure, let's check it, let's fix it. We have quite a few actually. Oh, of course, I forgot to type here, which is an easy fix. A very easy fix. What else do we have? I have problem here. Assignment read only variable read only because it's const. It shouldn't be const, of course. Yes, it shouldn't be const. And here, the return type is int. Oh, of course, I should do like this. I'm a dumbass. No internet. Yes, actually, there were no internet back then. Also, internet was already in the works. How soon did you get the internet as a military and defense worker back then? Unused variable divisor W. And yes, it is unused because we don't care. And why don't we care? Oh no. Oh no, hold on a second. We need to set this to that. This is correct way to do it. So now this should work. Okay, so we have no more errors. And let's go back to our bring up example and let's run it. Still errors. Where are they? Where are they? Bring up H. No such. Okay, we deleted this. Any other errors? Nope. We are green to go. And if we are green to go, let's see. Let's flash. So I expect if everything works correctly, that top LED will be always on and bottom LED will be blinking slightly because it's powered on in reset state. So let's see. Yes, exactly what's happening. Our D1 is always on and our D2 is blinking, but for whatever reason it blinks in odd pattern. I would assume it should blink like all the time. Not sure why this is happening. Actually, let's add a delay before we enable watchdog. 1 second delay, just to make sure that we have a stable blinking. Like this. And let's test again. So we will have a blink roughly every second. We were still using microfiche and paper regulations. What is a microfiche? Sorry for not knowing. Let me Google this one. Okay, why is my answer is in Polish? Scaled down reproduction of a document typically is a photography film. Or I'm sorry for being too young to know this. Photography film or paper made of the purposes of transmission, storage, reading, and printing. Okay. Scaled down reproduction. Oh, so I see. Yeah. Being you just talking to two guys who have no idea what the microform is. But it sounds like it's like old photographic tape, which I know about, which you can put in some device and it will be increased on your screen. So I get it now. Now we know. Now 2 more people know what this is. So let's test again. And we should have a blink on D2 roughly to... Does it look like once a second? It roughly does, so I would assume it works correctly. I see, I think my parents might still have had some at their workplace. What, were your parents also involved in something like government, high stakes jobs? So this works. Now let's see if we can reset it effectively. So let's say that this will be 50. Let's see, let's put it to 150 if it works. I'm not sure if it will. We will check the error log. Let's put it to 100. And here, let's toggle instead of turning on. And we should see, hell no, just government, no high stakes. I see. Also, I think I forgot personally function. I learned Fortran on punched cards. Oh, Fortran on punched cards. Wait a second. So Fortran was still on punch cards? I thought that punch cards are like were when you had to use the like bytecode directly. Oh, maybe you were writing on like computer, but then you had to convert to like the tapes. Because I would assume that Fortran should have already run on computers that can compile and run the code themselves. Maybe I'm wrong, actually. I'm not sure. But yeah, this is quite a long time ago. So what was my idea is to make sure this works. We can actually just calculate using our Wolfram. So let's do this. This is, hold on a second. Okay, let's test 150 multiplied by 500, 150 again, multiplied, no, by and divide by 4096. I definitely forgot a number. That was 1982. I see, makes sense. That makes lots of sense. And what number did I forget? 150 multiplied by this and divide by, I forget no number. Then I moved on to a VAX with a VT220 terminal. I don't know neither VAX nor VT220. Actually, is VAX a programming language? Assembly language, primary assembly language used for the VAX virtual address extensions. Okay. And VT220. Oh, that looks quite civilized. Images. That looks very civilized. Okay. Oh no, it's 5,000. So it says a possible value. Can we do 200? Oh, we can do 200 as well. My first electronics card system was an Apollo workstation. What? Apollo workstation is a name, or were you working on Apollo, like something from the Apollo era? Wait, hold on a second. Apollo workstation. 1P. Work in 1S. Wax used to be sold by Digital Equipment Corp. Apollo computer. Oh, I see. So it's just a computer name. Oh, quite nice, quite nice. Okay, so this is an acceptable number. So let's actually go for 200 here then. I see now, I see. And 200 here. And here we will put what exactly? One moment. One moment. Let me check one thing. Checked. Everything is fine. Apollo seems to have been an overloaded term back then. True, very true. Because my first thought was about like a space program, not about the personal computer. Okay, like this. So we should see a rapid blinking. But yes, I forgot to implement the function that will reset the watchdog. So let's get back to our implementation and implement the function that will reset the windowed watchdog. So it will be static force in line, void watchdog v reset void, and this should be a one-liner. Same, I also thought of Apollo mission. Its OS was similar to Unix, proprietary, I assume. I would assume so as well. That is a proprietary stuff. So it was already a Unix-like OS. So you are a Linux user. Okay, and let me open the datasheets to see what we should change here. Where is my datasheet? It's here. So to reset it, I need to is activated, is set, and then send boot is determined. The application program must write in the register at regular intervals during normal operation to prevent MCU reset. This operation can take place only when the counter value is lower than or equal to the window register. Okay. We need to write to SR at anything. So we need to do AVDG, CR, and we need to write something. So what do we write there? Let's open the register to see. So what can we write to CR? Oh, so we need to store this. So this value has to be stored somehow. That's actually annoying. That is actually annoying, which can not allow this function to be an inline one, but rather So because I have to store this, anyway, I got to go to work tomorrow, so I will be on my way, but I'm glad to have got you live today and finally follow you. Thank you so much for the follow and for the donation. I appreciate it a lot. Thank you so much for watching. Good night, and see you in the next one whenever you will decide to come. Bye-bye. So we should write this as a proper function because we have to store the value. And then this function should go here. And what we will do in this function is we will write this equals to, hold on a second, but this will be stored, right? Oh no, it will be changed, right? Hold on. These bits contain the value of the watchdog counter, decrement every, so they are decrementing, so I need to provide them. So this means that I need to write this plus the value I have to store. And the value is this value, so I need to move this to the global namespace. And now I can utilize it here. But I need to utilize it in a correct way, which is -1. And bit shifted, of course. Bit shifted to its correct position. Oh no, it is not this position, it is this position. Okay, so this should reset our watchdog properly. So let's test it. And let's see if it works as expected. Let's see if it actually works as expected. So we need to call it here. So it will be watchdog W, reset, done. And we should see our D1 blinking rapidly. So let's see. And let's run it. Yes, and after 1 second delay, it blinks rapidly, and it blinks rapidly because we set watchdog in time. So perfect, it works. It works as expected. Time duration is as expected. So now let's test the window functionality. So let's copy this code so that I can have it as an example to put into an example later. So it is actually an example 2 for windowed watch for VVDG. Here. So how do we check our window? We, let's say, set it to 100. And here we use only 50. And the reset will be too early. And that will force the reset of microcontroller. And because of that, we will see exactly what we saw before, which is that our D2 will be blinking roughly every second. So let's see. Let's see if it works as we expect it to. And let's run it. So our D1 is on and our D2 should be blinking roughly every second. Oh, will it? It doesn't blink, but also D1 doesn't turn off. So the watchdog works. We just don't see, maybe D2 is broken, given that I'm not sure if it's supposed to be like this. But yes, our reset is happening for sure because D1 stays on. It stays always on, but actually the easier way to... Oh, hold on a second. Am I stupid or am I stupid? Am I stupid or am I stupid? So maybe I should put it like this and like that to give it roughly more time, just in case D1 is blinking and we just don't see it on 20 Hertz. So let's switch it to 10 Hertz. 10 Hertz is definitely seeable on the LED by a naked eye. So let's run it. Okay, so it doesn't work then. Then I am stupid. So it doesn't work. And why doesn't it work? Do we have any errors in our error log? Do we have any errors? We don't. So no errors were caught. No errors were caught. Do we need to... Let's check actually register values. So let's stop it. And let's go to our watchdog registers, which are here. And by the documentation, we should see some value in W that we set up during our initialization. So 69 noise, but 69 is what in binary? 69, it's hex. 69 hex. It is 1101101. Okay. So it will be 105 minus 64, so it's below 64, so this is correct setup. But this should be 1, and this should be bigger as well. I would assume this doesn't seem like a correct setup, no? This looks very awkward. Oh, no. We have 1 here and 7 here. This is correct. So these are separate values, and this is a full register value. Okay. Then the implementation is correct. Now, how to use it is the question. So the question is that we need to... At what point do we need to reset to actually caught an error here? And for that, let's actually see the code. And see my other example. Let's stop it. Let's see the example we've done like an hour ago for the independent watchdog. And for independent watchdog.
Created _ just followed.
Thank you, Created, for following. I appreciate it a lot. Thank you so much. So our example without reset, which is example 3, says what? That we are trying to reset earlier than our window is set up. But this is exactly what we're doing. And how it's supposed to be working? So we are saying that our watchdog, let's say for this example, we are saying that our watchdog will trigger by itself in 1000 milliseconds. And we set a window to 500. So if it's triggered below 500, it should be an error. It should be a reset. So the same logic must apply to this example. When we set up our watchdog to 200 milliseconds, and if it triggers below 150, it should be an error. But it doesn't seem to be one. I think that implementation should be correct. No, maybe it's not. But let's see if I understood it correctly. So let's see the chapter. Let's see. Introduction. Sure. I don't need an introduction for now. Okay. Normal operation. This operation can take place only when counter values we just read it. Enabling the watchdog is always disabled after reset. It's enabled by writing we did it. When user option with the hardware window watchdog, the watchdog always enabled after reset. No, thank you. For now, it's free running, counting down. Okay. Bits contain the number of increments that represent the time delay before the watchdog produces a reset. Timing varies between a minimum and a maximum value due to unknown status. Okay, sure. can say the highest limit of the window. Sure, to prevent a reset, of course. Must be reloaded when the value is lower than or equal. Actually, maybe I do have an error. Let's see. Let's actually refresh it, and maybe my check is wrong. I kind of think it is actually. I actually would like to check the software right away. It runs the Apollo operating system, Apollo domain. What is Apollo domain operating system means? I'm not exactly sure. So let's see an error checking here. Here. And the error checking is that the reset duration should be smaller than this. And here we should do a similar check. Over here. Yes. But this will get a log error, but we don't have an log error. Okay. Am I confused now? I am confused, definitely. Why is it working? So it's blinking, but it doesn't supposed to be blinking. Because I'm resetting it too quickly. Where the hell am I? Because I'm resetting it too quickly. Why is it working? Or rather, why is it not working? As expected. Let's try even faster reset. Maybe my math in the implementation itself is wrong. I hope it isn't, but it may as well be. And run. It still blinks. Very interesting. So it still blinks. So it didn't help. And it seems like our windowed watchdog works without a window for whatever reason. So, and our error log doesn't show any errors, right? Yes, no errors here. Actually, do I suppose to edit here? Maybe this is an error. Let's open the datasheet. I'm not sure if I have to put one there. It's also a 7-bit register, which says what? 7-bit window value. This bit contains the window value to be compared with the down counter. Okay. And also, no, this is fine. Oh, I'm confused. High limit on the window to prevent a reset. No, I got this point. Okay. Okay. This chapter is like 3 pages. Hello. Must write in the normal operation. Let's try to remove this actually, and let's see what happens. And whatever happens, happens, as they say. Whatever happens, happens. Let's copy and let's comment out and let's remove this part. And let's try again. I don't think I make any huge mistakes. No, but this should not work, right? Was? It worked? What? What? What the hell? It works now? And let's say this will be 160, and this should start blinking. If this works. I'm confused. Run. So it doesn't work. So it still resets. Okay. What is going on? That's annoying. That's very annoying. And let's say I put it to 200. And let's see if it works now. If it doesn't work now, then we need the line that we removed. We need the part that we removed. So let's see. It still doesn't work. So the part was needed. The part was needed. Abort, abort. Change. Okay, but why isn't it working correctly? So our APB prescaler should be calculated correctly. So let's just use our lower debug level, debug optimization level 0, so that we have no optimization for this function. And let's compare this function to our Wolfram Mathematica values we expect to see. So let's put a test point here and let's restart it. What? What was that? Hello? Oh, okay. What? Yes. What? Oh, yes, it was working because it was resetting itself, and that's why it got to this point, because it calls every time it resets. Sure, that makes sense. Now let's run. We hit the test point. Now let's see our expressions, no, variables, and let's see the values. So we expect the, actually, let's switch this to 150. And let's see what happens. So we jump here, jump here, jump here. Jump here, and we get 150k, which is correct. So here, at this point, we get what value? 7324, which is what we expect exactly. Sorry, I need to sneeze. Every time I say that, I don't sneeze. Okay, so here we have this value, and we are at this line. And we will add 1 to this value, correct? Yes, we added 1. Perfect. These values are set. So this will not be the case. So we are here. This value is bigger, so we go inside. Perfect. We divide by 64. This makes sense. Then we go here, we plus 1. Still makes sense, still makes sense. So let me actually make it bigger. Let me make it bigger. So here we go in a loop. No, no. And we find the first power of 2 that is bigger than this number, and the number is 115. So we need to find 128. So we will go for a few circles, and we find what? Hold on a second. What? 64. Did I make a mistake here? Hold on a second. So we start from 0. Plus 1 in for loop is happening only after the cycle, right? Actually, go to hell, for loop. While this this number will go up in the end. Okay. Let's try again. We returned, and actually maybe there was a loop error. I actually haven't written loops for so long that I make errors in loops, because loops are not widely used in embedded at all. Holy, that is shameful. Okay, so let's say 150 here and 100 here. And let's see. This should reset microcontroller, so we need to see D1 being always on. So let's see. And D1 is blinking, so it doesn't work. So let's put our test point back and see what is wrong. Because it's supposed to be resetting the microcontroller and it doesn't. Okay. We go here and we will actually put the test point here because this is the last time we had an error in calculations. I have to go too. This was fun. Thank you for sharing your frustrations. Thank you for being here with me with my frustrations. Thank you for watching. Have a great, I would assume, like rest of your day, evening. And see you here anytime you wish to come back. Bye-bye. Okay, so let's run. We hit the test point, breakpoint rather, and we go. So current divider is this, and initial div is this. Okay, so we go again. Current divisor is 8, sure. Oh, I know, I'm such an idiot. Fuck me. Because this is a reasonable value as well. Oh my god. Oh my god. I'm such a stupid person sometimes. So now it should work, and let's remove the breakpoint. And let's run it, and this should be resetting. It resets. Okay, now it works. And it should not reset here. So now when we flash it, it should be blinking actively. And let's run it. Was! Still resets. No, why? Still resets, so something is still wrong. Something still makes no sense there. Okay. And 170 didn't help. Yes, so then we put the breakpoint back and see what number we have here. So let's go again. We run, we jump, 16 here, 32, 64, 128. And at this point, we break the loop. We get here. So what do we get here? At this point, jump 57, which should be converted to 58. Very nice. And we set it to T, which is correct. What? Oh no, it's correct. There will be no error. We calculate this value to be that. Okay, sure. We calculate this value to be 42. And let's test it. So at this point, we should have 42 multiplied by 128 multiplied by 496 and divided by 150,000. And this should give us a delay of 146. Okay. So 42 is a correct value we expect. Why were you jumping so many times? So we are at 69 again. Yes, and 69 is 42 plus 64, 43 plus 64, right? Because it's 105, and 64 plus 43. Wait, it should be 107. Oh, minus 1 here as well. And we also don't do the plus 1 here. So yes, it is correct, 69 noise. So the setup is correct then. But why isn't it working? So run it. And it resets microcontroller when it doesn't supposed to. Because we are resetting in the correct frame. It doesn't supposed to reset the microcontroller. Why does it reset it? Okay, let's run. Let's remove the breakpoint, of course. Something crashed or not? What is happening? Nothing is working. That I can say for sure. Reset again. We go again. And run it. And it resets. Oof. That's annoying. But maybe I don't understand how it's supposed to be working. What if I say 50 here? That's annoying. It still resets. So it resets anyway, like both ways. I'm confused. And I actually have no idea now where to look for why this is happening. Because I believe that I set the values correctly. And the chapter is like 3 pages long. So I think that the next thing you do in this situation is you go and look into the whole. Like unless you wish to go and use AI, but if you don't want to use AI and you are a hardcore bare metal developer, at this point you go and set up watchdog in the whole of STM32 and see their implementation. You dive deep into the CMCs, but I don't think I will do it today because these take quite a while and I'm very tired. So I will finish for today then. I will fix this bug later, tomorrow. Thank you everyone for watching. I appreciate it a lot for everyone to be with me through my struggles. Follow if you're not following and we would like to see more. I appreciate the support a lot and see you everyone in the next one.